Welcome to Efiwe, excellence without stress.
Hello guys, it's your favorite chemistry tutor, Godson, and this is Efiwe, excellence without stress. Today we are going to be learning something interesting. We actually do learn something interesting in every class, but today's one is quite special. Now, how many of you had to go through a particular process over and over and over and over and over again, as if you are literally walking in cycles? I guess it must have been very tiring for you. Some chemical reactions actually have such experience, but they never get tired, especially when the process is said to be in equilibrium. Such reactions are referred to as reversible reactions. Now, we're not going to be laying emphasis in this video on the reversible reactions, but on what keeps those reversible reactions going over and over and over without getting tired. So let's get into it, discussing chemical equilibrium. So our study today is going to be shared into three different parts. The first part is the introduction to the concept of chemical equilibrium. Then we get into our understanding of chemical equilibrium constant and its derivation. How did we get that particular constant? And finally, we are going to be talking about Le Chatelier's principle and the effects of external constraints. Let's go ahead with our study. The very first question that needs to be answered is, what is chemical equilibrium? But before we get into chemical equilibrium, a system is said to be in equilibrium when there is no observable changes in the system over a given time interval. So once you notice that nothing is literally changing, for instance, you place two children of the same masses on the seesaw, or what we used to call jangilova at that time in our Bako primary schools, you get. So when two children of the same weight are placed at the extremes of that particular seesaw, you will notice that there should be no movement. That is equilibrium. However, chemical equilibrium is said to occur if the rate of forward reaction is exactly equal to the rate of backward reaction for a reversible process. So just have that in mind, that anytime you are asked when is chemical equilibrium said to occur, it simply is said to occur when the rate of forward reaction is exactly equal to the rate of backward reaction for a reversible process. The implication is that if the process is not reversible, you ain't going to talk about chemical equilibrium. You only talk about chemical equilibrium for reversible processes. Now, this particular statement I just made is also known as the equilibrium law or the law of equilibrium. So moving ahead, we have mentioned reversible process when we started the class, and we are mentioning it again. So it's high time we talk about it. A reversible process is one which can be taken from its initial state to another state and then back to its initial state without any change to either the system or the surrounding. So when a particular chemical process seems to be going back and forth, to and fro, to and fro, to and fro, you refer to it as a reversible process. In chemistry, such processes are usually identified by two arrows going forward and backward. So mind you, once you see a chemical reaction that is written, okay, let me just put down one. Let's go to our writing screen. Here's the writing screen again. So take the slide out. Okay, and yes, voila. So back to our writing screen. As I was saying, I said that once you consider a particular process and notice that you see a forward arrow and a backward arrow, that is the implication that it is a reversible process. So for some of you that are about to ask, how do I know if a particular process is reversible or not? This is your answer. Once you notice that this reaction has a forward arrow and a backward arrow, it is said to be reversible, which means this would react to give the product, and then the product would eventually go back to form the reactant. So this process will keep going on and on and on and on, and this is basically a reaction to produce ammonia when nitrogen and hydrogen directly combine. Okay, so that's that basically. I'm just trying to show us an example of what we mean when we say a process is reversible. Okay, with that said, let's bring back our slide. Okay, so having said that, the very next thing we are going to be discussing is to consider a particular question. Equilibrium is said to be attained in a reversible reaction when what happens? Option A, all the reactants have been used up. Option B, all the products have been formed. Option C, there is no further change in temperature. Option D, the rate of forward and backward reactions are equal. Option E, the rate of formation of the product decreases with time. What is our answer? Option D. Because it was just stated that when the system is said to be in equilibrium, the rate of forward reaction is exactly equal to the rate of backward reaction. So, with this said, we are going to be concluding our introduction to this concept. And in this section of the study, we are going to be discussing equilibrium constant. As I was saying, equilibrium constant is a very important concept to understand. Major reason is because it has a lot of applications and you will find it in so many places in your chemistry study. You see it in relation to pH, you see it in relation to your Gibbs free energy, you see it in relation to your electrolysis and so many other parts of chemistry. So once you understand this concept now, it kind of makes it easier for you to move on with the studies when you see it elsewhere. So as I was saying, we are discussing the concept of chemical equilibrium constant. So what is the equilibrium constant referred to as? Equilibrium constant is the ratio of active masses of products to the active masses of the reactants. Yes, you are seeing a strange word, active masses. We'll get to that. But before we get to that, you have to take note of the fact that it is derived from a combination of two laws. The law of mass action and then the equilibrium law. These are the two laws that when you put them together, your understanding of these two laws would help you derive this very important constant known as the equilibrium constant. Now, as I was saying, it is a ratio of active masses of product to reactants. But then we don't know what the active masses are. So let's look at what an active mass is. So when you consider an active mass is the concentration of a substance raised to the power of its coefficient in a balanced equation. I take it again. An active mass is the concentration of a substance raised to the power of its coefficient in a balanced equation. So to help us understand this, I think I would have to write when you consider the active mass of a substance, imagine you have a reaction A plus B. Okay, let's introduce coefficients, or coefficients, which includes the number of moles, but let's call this MA is reacting with NB, and then it gives PC plus QD. If you are asked to find the active mass of a substance, according to the definition, it is the concentration of that substance. Remember that concentration can also be represented as square bracket. So the concentration of that substance raised to the power of its coefficient in the balanced equation. In this balanced equation, I forgot to make it reversible. Yes, equilibrium constant only appears in reversible processes. So just have that in mind, that once it is not reversible, it is not going to have an equilibrium constant. Anyway, let's continue. So the active mass is the concentration of that substance raised to the power of its coefficient. So this is going to be concentration of A raised to power M for the active mass of A. Active mass of A. If we are now asked to find the active mass of B, that's going to be quite simple. The concentration of B raised to the power of its coefficient in the balanced equation N. What if you are asked to find the active mass of C? The active mass of C is going to be the concentration of C raised to the power of its coefficient, which is P. And what if you are asked to find the active mass of D? The active mass of D is going to be the concentration of D raised to the power of its coefficient, which is Q. So you have that in mind, that whenever you are asked to find the active mass, simply do concentration of that substance raised to the power of its coefficient. So if the concentration of A, let's say I have a reaction. Let's say it is now 2A plus C reacting to give 3B plus 5D. If the concentration of A is 0.1 and I say what is the active mass of A, it is now going to be 0.1 all raised to the power of 2. If the concentration of C is 0.7 and I ask you for the active mass of C, you will simply do 0.7, that concentration raised to the power of its coefficient, which is is now 1. So basically, that is the whole concept behind the active mass. Now, with this said, let's go back to our study in the slide. Okay. Having understood the active masses of a substance, the next thing we are going to discuss is the law of mass action. Why? Because, as I said, in describing or understanding equilibrium constants, there are 2 laws that are very important. One of them is the law of mass action. And what does the law of mass action state? The law of mass action states that the rate of a chemical reaction is directly proportional to the active masses of the reactants. The rate of a chemical reaction is directly proportional to the active masses, not of the products, but of the reactants. So please do not make that mistake of misplacing the 2 of them. So let's kind of take this out so we can be able to explain it on our board. Now, if for instance you have let's say you have a particular process, let's still use our A and B. So MA plus NB reacting reversibly to give PC plus QD. Okay, now for the forward reaction, the rate at which the forward reaction is occurring is R1, while the rate at which the backward reaction is occurring is R2. Now, mind you, a reactant is the beginning or the starting materials for the reaction. These are the reactants for the forward, while this is the product. But when we are now going back, you will now notice that this particular part is the reactant, while this is the product. Product is where the arrow is pointing to. Reactant is where it's coming from. So for this second arrow, where is it starting? Where is it going to? It's going towards this side. So this is the product for the second arrow. But where is it coming from? From C and D. So here is the reactant for the backward. But for the forward, this is the reactant, that's the product. I presume this is quite simple because, you know, we all have quite excellent understanding of this concept. So let's continue. Now, having said this, the next thing we have to do is to apply the law that we just mentioned. The law of mass action states that the rate of a chemical reaction is directly proportional to the active masses of the reactant. So for R1, it has to be proportional to the active masses of A and B. So let's put that active mass of A is A, concentration raised to power M, multiplied by the active mass of B, which is concentration of B raised to power N. So you have that. But for the backward reaction, R2, you will notice that the reactant will be C and D. Hence, we can now say concentration of C raised to power P multiplied by the concentration of D raised to power Q. And that's that basically about the law of mass action. This particular expression describes it. Now, if we are to apply mathematics principle, you will notice that you are supposed to remove this proportionality sign. And when you remove a proportionality sign, you introduce a constant. So R1 will now be equals K1 concentration of A raised to power M multiplied by the concentration of B raised to power N. While on the other hand, you have that R2 will now be equals K2 concentration of C raised to power P multiplied by the concentration of D raised to power Q. So mind you, K1 and K2 are constants which are referred to as velocity constants. Velocity constants. It's important you take note of this. So have that in mind that this is the first part of your understanding of the equilibrium constant derivation. Now let's continue. Having mentioned this, the next thing we are going to do is to go back to the slide and continue with our discussion. The next law that is applied for us to understand this particular equilibrium constant or derive it is the equilibrium law. And I presume everybody knows the equilibrium law because we stated it in the earlier video. So the equilibrium law states that a system is said to be in equilibrium if the rate of forward reaction is equal to the rate of backward reaction for a reversible process. Or you could say it is said to be in equilibrium if the rate of forward and backward reactions are equal for a given reversible chemical process. With that said, we are going to go back to our board and then discuss this in details. So once the rate of forward reaction is equal to the rate of backward reaction, automatically you are referring to a system in equilibrium. So we can say that for this system to be in equilibrium, R1 has to be equal to R2. This is what we refer to as equilibrium law. Now, I want to take this whole thing out so that we can just continue, basically, have more space to solve. Okay, now having taken it out, I presume you noted what we discussed earlier. So we said that for this system to be in equilibrium, R1 has to be equals R2, and when that happens, it means that K1 multiplied by concentration of A raised to power m times concentration of B raised to power n will now be equals K2 multiplied by the concentration of C raised to power p times the concentration of D raised to power q. Mind you, and remember, this is equivalent to these two guys over here, as we saw in the earlier derivation. Now, having gotten to this point, the very next thing you need to do is to rearrange it. And when you rearrange it, you'll find out that K1 over K2 is going to be equals concentration of C raised to power p multiplied by concentration of D raised to power q divided by concentration of A raised to power m multiplied by concentration of B raised to power n. So mathematics students, you can do your cross multiplication and you find out that this whole equation is still the same thing. I just rearranged it. Why did I rearrange it? Equilibrium constant, which is K of C, is equals K1 over K2. And when you have that it is equals K1 over K2, it means that the equilibrium constant of any reaction will now be given as the active masses of the product, which you noticed in this case is C and D, divided by the active masses of the reactant, which you notice in this case is A and B. So just have that in mind. Now once they ask you for the equilibrium constant of a process, all you need to do is the active masses of the product divided by the active masses of the reactant, and that is your answer. Now, we are going to be trying some questions out, but before we try those questions, there are very important points that must be noted in our study of these concepts. Very important points that must be noted, and we are going to be considering them one after the other. So what are the points to note? Let's see. Bring that so that everybody can see it. The points to note are very simple. The first one is that the active masses of solids and liquids are usually equals 1. So once you have the active mass of a solid or a liquid, it is usually equals 1. Have that in mind, that for most cases, especially in your O-level questions, once they give you a solid or a liquid in a particular reaction, just equate its active mass to 1. The second point that must be noted is that the species involved in equilibrium constants are aqueous ions or solutions and gases. You will not see a solid or liquid in most cases when you are dealing with. The only liquid you see is if the liquid is an aqueous solution. So once it's an aqueous solution, aqueous solutions are represented by AQ. So have that in mind, that once you see an aqueous solution, a gas or an aqueous ion, automatically it is supposed to be part of the species involved in determining equilibrium constant. But if it is a solid and liquid, its active mass will be equivalent to 1. Then the third point is that equilibrium constant for the forward reaction is the reverse of that of the backward reaction for a given reversible process. I think I might have to just quickly just express it or explain this briefly on the screen. So let's go back to our screen. Now, I can take this out. Remember we said that anytime we are asked for the equilibrium constant of a process, it is simply the active mass of the product all over the active mass of the reactant. So let's do this together. So if you have a reaction, let's use that reaction we had. A plus B, this is Mn reacting to give reversibly C, P plus D, Q. Okay, so if we are looking at the equilibrium constant for the forward reaction, it is going to be the product. Forward means that this is the product and this is the reactant. So product, active mass of C raised to power P. Okay, that's an error. P multiplied by the active mass of D raised to power Q, all divided by the concentration of A raised to power M multiply the concentration of B raised to power N. Now, for the reverse process, A and B are now the product, so which means the equilibrium constant for the backward process will now equals concentration of A raised to power M multiplied by the concentration of B raised to power N, because it's now the product backward, divided by the concentration of C raised to power P multiplied by the concentration of D raised to power Q. So in this case now, you will notice that if you do 1 divided by this, it will give you this, which means K of C for forward is equals 1 divided by K of C for backward. Very easy. So just have that in mind, that if they give you a question and tell you that the equilibrium constant of the forward reaction is 2, what is the equilibrium constant of the backward reaction? Please simply do 1 over 2. That's the answer. If the equilibrium constant for a forward reaction is 2 over 5, it means that the backward will become what? 5 over 2. So have that in mind, that the equilibrium constant of the forward is always equal to the equilibrium constant of the backward. Then we go to our final point. The final point we are going to be talking about is that the active mass, okay, so we have that in a reaction is said to be in equilibrium if the change in Gibbs free energy is equal to 0. So once you notice that in that question or equation or expression, they tell you that the change in Gibbs free energy is equal to 0, automatically it implies that it is in equilibrium. That's the G. Once you see in a question the G is equal to 0, the implication is that that system is said to be in equilibrium. Let's try out some questions to buttress our understanding of this concept. So, in what way is equilibrium constant for the forward reaction related to that of the reverse reaction? Option A, addition of the two is expected to be 1. Does that make sense? Probably, but that is not the answer. Option B, the product of the two is expected to be 1. Option C, the two equilibrium constants are identical. No, that obviously is the wrongest answer there, because they are not identical. We can actually see that. And then finally D, the product of the two is always greater than 1. So let's get to see why or which of them is the correct answer. Now, if you look at the screen, already we have answered this question by this expression. This expression has given us our answer. So let's look at it. If you have that Kc of F is equals 1 over Kc of B, cross multiplying the two of them, you will notice something. Kc of F times Kc of B is going to be equals 1. So what is this trying to tell us? That the product of the equilibrium constant of the forward times the product of the equilibrium constant of the backward is equals 1. They are not identical. This is C over CD over AB, but here is AB over CD. Identical means they're exactly the same, so they are not identical. If you add them, it won't give you 1, but the product of the two, as given by this expression, is definitely going to be equals 1. We can actually try it out. If you multiply these two things, you have that C raised to power P times D raised to power Q divided by A raised to power M times B raised to power N. If you multiply it with the other guy for backward, which is A raised to power M times B raised to power N divided by C raised to power P times D raised to power Q. Now notice something. This D cancels D here, 1. B cancels B down, 1. C cancels C up, 1. 1, 1. So this is going to be 1 times 1 times 1 times 1, which is equals 1. 1 times 1 times 1 times 1, which is equals 1. 1 divided by 1 equals 1. So when you do the product of two equilibrium constants, that's reversible equilibrium constants, you have that the value is going to be equals 1. Okay, so we've answered that. Let's move ahead. The next question we're going to be trying out is, for a reaction in equilibrium, the species involved in equilibrium constant expressions are A, gaseous and solids. If you go back to what we discussed, look at the second point. The species involved in equilibrium constants are aqueous ions or solutions and gases. So those are the two things you are looking out for. So you have that here. They said gases and solids. Gas, correct. Solid, wrong. So two of them cancels out. B, liquid and solids. Obviously not. Completely wrong. C, solids and dissolved species. Come on. Dissolved species are actually aqueous solutions. So have that in mind, that if you don't see aqueous solutions, you are likely going to see dissolved species. And that is option D. So gaseous and dissolved species is going to be an answer. However, an aqueous solution is a solution whose solvent is water. Always have that in mind. Then we go to the next question. Which of the following equations shows that a reaction is in equilibrium? Obviously, it is D. Because we said that once your Gibbs free energy is equal to 0, the system is said to be in equilibrium. The final question for this particular section of the study is this. what is the expression for the equilibrium constant Kc for the following reaction. So we are going to like get to take this out of the screen and then go to our board and then play around it. Okay, so let's take everybody out. Everybody leave. Okay, so writing our equation, the equation is, let's see, what's the equation again? So the equation is N2 plus O2 reacting reversibly to give 2NO. And once we do that, what do we have? So we have that N2 plus O2 reacting reversibly to give 2NO. And we're asked to find, note that this is a gas, this is a gas, this is a gas, because if there was a solid, we are not going to use it. Okay, so reversibly reacting, what do we have? Now, if this is reacting reversibly, what is going to happen here is that equilibrium constant is equals product over reactant. What is the product? This is the product. So what is the active mass of the product? Concentration of NO, which is the product, raised to the power of its coefficient, raised to power 2, divided by concentration of the reactant, so concentration of N2 raised to power 1, concentration of O2 raised to power 1. Now, because these things are gases, we will not convert any one to give 1, which means we are going to leave them as they are. So this is the answer. So let's look at what option is equivalent to this in our question. Let's bring him up. Okay, our slide should come up right about now. A is obviously wrong, majorly because it has n raised to power 2. B is wrong, C is wrong. Okay, now the correct answer there is D. Why? Remember that the power you are raising is the concentration, the whole concentration, all raised to the power of 2. So the implication is that the 2 has to be outside the concentration box for it to be that power. Now, if you notice, there seems to be a typographical error in option D. Just have it in mind that that 2 is supposed to come down. So generally speaking, this is basically how to resolve your equilibrium constant questions. Welcome guys to the last part of the study in chemical equilibrium. Remember, this is a ride with Efiwe, excellence without stress. And I remain your favorite chemistry tutor, Godson. In this part of the study, we are going to be understanding a very important work by a very great scientist known as Le Chatelier. Now, he stated a principle which states that if a system in equilibrium is affected by external constraints, such as change in pressure, concentration, or temperature, the equilibrium position of the system shifts in order to annul these effects. How do I put this? If, for instance, you have that a particular effect occurs on one end, the system begins to change itself so that it will restore back that equilibrium. Let's consider this particular condition or situation. For instance, let me take the slide out so we can all see my illustrating board. Okay, yes, I presume you can see the board now. Okay, so over to this. Now you will notice something. If, for instance, I tell you that a particular system is in equilibrium, and I tell you that the value for equilibrium is 10. Now, and then maybe something happens to the system and pushes that system up to 20. What the system is going to do is to drag it from this 20 down back to 10. So just have that in mind, that anytime a particular process occurs to change the position of a system, the system will restore equilibrium by doing the reverse or opposing it by any of the actions it seems or deems fit for that process to be restored. Take, for instance, you have a seesaw. I call this Jangelova theory. It's not an existing theory. It's just one concept I used to explain this. So you have a box here and a box here. If these two boxes are of the same mass, let's say 5 and 5, this system is supposed to be in equilibrium. But once I put an extra 5 box here, automatically this is going to tilt the system and change its equilibrium position. So you have that the system will no longer be in equilibrium in this state. So what is going to happen? The system, after looking at this condition, would have to do something to bring it back to equilibrium. What the system does is to add another box on this side. And once you add another box on that side, you have restored the equilibrium. So you now have 2 boxes here of the same mass and 2 boxes here of the same mass. And once that happens, this system's equilibrium is restored. So my point is that the system just changes things and makes things happen to make sure that equilibrium is restored at every cost. Having said this, let's consider the different constraints that affect equilibrium and how these things affect a system in equilibrium. So we're going to start with the first one. Let's get our slide open. We're going to start with the very first one. And that first one is, effects of change in concentration. But before we talk about that, there are 3 notes here for us to have in mind. If the equilibrium position shifts to the right, it favors the forward reaction to yield more product. If it shifts to the left, it favors the backward reaction to yield more reactant. And finally, catalysts do not affect yield in any way. That is to say, they do not give more products, neither do they give more reactants. They only alter the rate of reaction. So if you see a question that has to do with yield and they say which of these factors affects the more production of the product or yield of the reactant, catalysts do not have anything to do with yield. The highest they can do is that they can alter the rate, make this particular process occur faster or slower. Let's move ahead. Let's consider how change in concentration would affect the equilibrium of a system. If the concentration of a reactant is increased, the equilibrium position shifts to the right to favor the forward reaction and yield more product. For us to be able to understand this and not just cram this, I would illustrate using what I call my Godson's Jamb theory. It's not an existing theory, it's just a concept I used to explain this. Now, just as I said, we used to call this thing the Paco children. We call this thing Jamb, but then it's the seesaw. Now, just as the illustration I gave before, if for instance I have a box here and another box here, and these 2 boxes are both 5 grams. Now let's call this side the reactant side and call this side the product side. Adding to the product is forward, adding to the reactant is backward, as we saw. Now this system now is in equilibrium, static equilibrium, is balanced. Now if by any chance I add something to this reactant side, automatically you will notice that the system would move and change its equilibrium position, and it would look something like this. So you would have 1, 2, and you would have 1. Now the common sense here is this: what side do we need to add something to in order to restore equilibrium? You will notice that for us to restore equilibrium, the system needs to add to the product side. So if you add to the reactant side, system adds to the product side. So just have that in mind, which means if you add to the product side, system adds to the reactant side. So let's take it again. Add to the reactant side, system adds to the product. But when you add to the product side, system adds to the reactant. So in this case, we added to the reactant, it tilted. For this particular situation to be brought back to equilibrium, system has to add to the product side. So this is where the system adds. And once it adds it, you will notice that equilibrium is restored. Now, mind you, when the system is adding to the product, it is favoring the forward reaction. So once you hear reactants are added to, once you add reactants to or increase the concentration of reactants, what it does is that it will make the system to add to the product side. And when the system adds to the product side, it favors the forward reaction. So always have that in mind. Favoring the forward reaction is caused by increasing reactant concentration. Because once you increase it, system will now go and be adding to the product, which is the forward reaction, in order to restore equilibrium. Okay, so let's look at our slide. Go back to our slide. We have that. Okay. Now, having said that, Okay, effects of change in concentration decrease. Before we talk about the decrease, let's come back to the increase and finish. So we said that if the concentration of the reactant is increased, the equilibrium position shifts towards the right to favor the forward reaction and yield more products. So if you add reactant, system will go and add to the product. That's the emphasis. Now, on the other hand, if the concentration of the product is increased, if you add to the product, the equilibrium will shift to the left, which is going to favor the backward process, and eventually you will notice that more reactants will be produced. So just have that in mind, that when you add to the reactant, system adds to the product, favoring the forward. But when you add to the product or increase the concentration of the product, what happens is that the system would add to the reactant. It's more like a vice versa thing. Okay, so let's continue. Now, if the change in concentration is now a decrease, let's see what happens. If the concentration of the reactant is now decreased, the equilibrium position shifts to the left to replace and increase the reactant, hence favoring the backward reaction. Let's see what this actually means. I'll have to take this out once more so that I would use our illustration. Where is our screen? Our screen is with us now. Okay, so let's kind of take this whole thing out. So once we take that out, we now look at this. Now look, imagine for instance, we have this system. We have two boxes and they are in equilibrium. This is the reactant side, this is the product side, this is forward, this is backward. Now we're dealing with decrease. If we decide to decrease this time around and remove this particular guy, you will notice that there will be more on this side and the whole system will fall towards this way. So which means that you are going to have it looking like this. Why? Because you reduce the reactant, automatically it tilts towards the product. Now, however, what will the system do to restore this equilibrium? Will it go and add to the product or go and add back to the reactant? Obviously, it will try to replace the lost reactant. And because it is going to be replacing the lost reactant, it means that it is going to favor the backward process. So have that in mind, that when I removed from the reactant, system replaces that one I removed. But when I add to the reactant, system adds to the other side. So that's the principle, that if you remove from a point, system replaces that point you removed. So if, for instance, I tell you that I removed a reactant, it would favor the production of that reactant. But when I add a reactant, the system goes to favor the addition on the other side. So basically in this case, when I remove the reactant, it falls like this. Then to restore equilibrium, system needs to replace that particular reactant I removed, which is favoring the backward process. So that's that basically, which means on the vice versa, if we consider what happens with respect to the decrease in product, you will notice that if the concentration of the product is decreased, the equilibrium position shifts to the right to favor the forward process and increase the product. So it's basically in removal. When something is removed, system will replace it, which means if I remove reactant, system is going to replace that reactant. If I remove product, system is going to replace the product. While in the case of addition, when you increase this side, system increases the other side. The conclusion of this whole statement is this: if I want a forward reaction to be favored, this is something you should take note of. To favor the forward reaction with respect to concentration change, increase reactant or reduce product. To favor the forward, increase reactant or reduce product. While to favor the backward, decrease reactant or increase product. I take it again. To favor the forward, increase reactant or reduce product. While to favor the backward, you decrease reactant and increase product. So that's that basically about how change in concentration can affect a particular system in equilibrium. Now, with that said, we will be going into the next one, which is the effect of temperature change. Now, reactions can either be endothermic or exothermic, and the effect of temperature is dependent on this fact. Note, if forward reaction is endothermic, the backward is exothermic and vice versa. So this is very important to note because it will determine our understanding of this concept. Once you say that a particular process is going forward and it is endo, the reverse process will be exo. If it is exo forward, the reverse will be endo. Very important. So let's get to understand what an exothermic reaction. That should be a big time typographical error. Now, an exothermic reaction is a reaction during which heat is liberated from the system. to the surrounding. So once a particular reaction or process occurs, like a combustion reaction, in most combustion reactions, heat is released to the atmosphere. That's why when petrol is burning or any other form of fuel is burning, heat is usually generated. You get? So that's that basically. So those reactions are said to be exothermic. They release heat to the environment. Now, the forward reaction of an exothermic reaction is favored by a decrease in temperature, while the backward is favored by an increase. Before we get to explain this, note something. Enthalpy change is always negative. Enthalpy change is always negative for an exothermic process. I would like to just do a brief description of what I actually mean by this whole thing. The basic thing I want you to note for this particular endothermic is this. For this particular exothermic reaction is this. Follow the signs. When you're considering temperature change, just follow the signs. If you have a reaction of, let's say, SO2 plus O2 reacting reversibly to give SO3, this is going to be 2, 2. This reaction is exothermic. Once you see a minus sign, it means that for the forward, you need to reduce temperature. I take it again. Follow the sign. Once you see that it is negative for enthalpy, decrease temperature. So minus implies decrease, while plus implies increase. So just have that in mind that for this process, this is going to be a negative enthalpy, which is exothermic. Follow the sign. Once you see the sign is negative, it means that to favor the forward process, you need to decrease temperature. Okay, what if I had said SO3 reacting reversibly to give me SO2 plus O2? In this case, the H is going to be positive. Now remember, for the forward reaction to be favored, I need to look at the sign. If the sign says plus, I need to increase temperature. But in this case where the sign says minus, the implication is that I need to decrease temperature. So just follow the sign and you are good. If you look at the sign and you notice that it is an exothermic process, automatically what do? The forward is favored by decreasing temperature, while the backward will be favored by the vice versa, which is increasing temperature. If you remember what we said, if the forward is exo, the backward is supposed to be endo. Okay, so let's try out the question to help us buttress this point basically. Okay, so the question says, what will happen if more heat is applied to the following system at equilibrium? More heat, that is to say, we are increasing the temperature. Now, normally, if you are increasing the temperature, it should be favoring the forward if it was positive. When you add more heat and notice a minus sign, it means that it's going to be backward. So have that in mind, that more heat means increase in temperature. But then because it's minus, to favor the forward, you need to decrease temperature. In the case of an exothermic reaction, once you see it is minus, you need to decrease temperature. But if you increase temperature, instead of favoring the forward, it's going to favor the backward. So which means the options we are looking for is that it is going to increase the amount of X2 or Y2, or decrease the amount of XY3. So let's look at that. Now it says the yield of XY3 will decompose. Before we choose an answer, let's go through all of them. More of XY3 will decompose. Let's still continue. More of X2 will react. And then finally, the forward reaction will go to completion. Now, option D is completely wrong because this is a reversible system and is in equilibrium, which means that it is going to continually keep going on and on. If you come up to option C, more of X2 will react. If more of X2 is reacting, it's favoring the forward process. But then this is exothermic. If you increase temperature for exothermic, it should go backward. Once it is exothermic, what you need to do is to decrease temperature. So option C is wrong. Then we have B. More of XY3 will be decomposed. Now, remember that backward reaction for XY3 is a decomposition reaction, and that is exactly what will happen. That once it is exo means that we are supposed to have minus here. And minus means that we need to decrease, remove heat. But when they are increasing the heat, it's now going to start going backward. So instead of formation of XY3, you are going to have decomposition of XY3, and that is the answer. Then option A, the yield of XY3 will be the yield means production of XY3. That's basically not what we are talking about. We are dealing with the direct decomposition of your XY3. So the most correct answer amongst all these particular options is your option B. Having said that, we go to the next question. What happens to the equilibrium constant of the reaction above if the temperature is increased? This too is a technical question, so let's do our analysis properly. The first thing I'm going to do is to try to write down the reaction so we can all see. Write down the reaction so we can all see it. So let's go to our board. Okay, so we'll take all these things out. So the question says we have 2H2O. Oh no, that's not 2H2O. That's 2H2 gas plus O2 reacting to give 2H2O. And you have that the H in this case is negative. So they said, what happens to the equilibrium constant? Remember that equilibrium constant is equals product over reactant. Have that in mind, which means if the product is increasing, the equilibrium constant will be increasing. But when the reactants is increasing, the equilibrium constant will be decreasing. So they said, what happens to the equilibrium constant of the reaction if the temperature is increased? Now, notice something. It is exothermic, which means if you are going to favor the forward process, what you are supposed to do is to decrease temperature. So if we are going to give more of the product, if we want to increase the product, we need to decrease. But since they increase temperature, it means that it's now going to give him more of the reactant. So which means more reactant. And once you have an increase in the reactant, notice what I said will happen. The equilibrium constant will begin to decrease. Why? The equilibrium constant is inversely proportional to the reactant. So if you look at the options, you find out that your answer is going to be that the equilibrium constant will decrease. Why? Because increasing the temperature for an exothermic will favor backward. If it was exothermic and you want to favor the forward, you need to decrease temperature. Why? Follow the sign. The sign says minus, which means decrease. And once you decrease it, favors the forward. But if you now increase it for exo, it means that it's going to favor the backward. In this case, favoring the backward means you are increasing the reactant. And as this reactant is increasing, the equilibrium constant is decreasing. That is why our answer is C, that it decreases. Okay, having said that, we would probably try, let's see how many more questions we have to try before we go to the next concept. Okay, so that's that basically about the exothermic question. Now, the endothermic process is basically the inverse of whatever you heard in endo, which means that for endothermic is going to be the endothermic process is the reverse of whatever you heard in the exo, which means that endothermic reactions are reactions in which heat is absorbed from the surrounding to the system, and the enthalpy has to be positive. Remember, if it's positive, it means that it is going to be favored forward by increase in temperature. I said just follow the signs. That's the trick I use. If I see minus, it means that I have to decrease temperature for forward. If I see plus, it means I have to increase temperature for forward. That's basically what I do, which means that if I now have a decrease for where I have minus forward, but if I have an increase in temperature for where I have minus, it means it's going to the opposite side. So basically follow the sign. Now, the forward reaction of an endothermic reaction or process is favored by an increase in temperature to yield more products and vice versa. So just know that once it is endothermic, it's positive, which means increase the temperature if you want more products. Okay, having said that, we'll try this question. Now, consider the reaction represented by the equation N2O4 reacting reversibly to give 2NO, and that is a positive enthalpy. What happens when the temperature is reduced? Now, normally, because it's positive, if you want to give products, positive means increased temperature, which means when you now reduce temperature, it will now go backward. So which means that you are going to have more of N2O4 and less of NO2. So let's check the option. Concentration of N2O4 would decrease. No, we have positive. If it's going to go forward to produce NO2, Positive means you need to increase temperature, but since you are decreasing temperature, it will go backward to give more of N2O4. So the concentration of N2O4 is supposed to increase. And if you look at your options, that is option B. Automatically, that is our answer. And that's that basically with respect to your questions with respect to endothermic reactions. Okay, now the next thing we are going to be considering is the effect of change in pressure. Before we understand, or in our understanding of this effect, the first thing we need to take note of is that pressure changes only affect gas yield. That is to say, if there is no gas in that particular process, change in pressure will not affect it. If you have a reaction that is reversible and there is no gas, change in pressure will not affect it. Let's take, for instance, this particular reaction. Let me just take this out quickly and have us resolve that. So if you have this particular reaction, let's say a reaction between methanol, which is a liquid, plus methanoic acid, an aqueous solution, which is going to give methyl methanoate and water. This reaction now is a reversible process. This is liquid and water is also liquid. Now notice that if there is a change in pressure in this type of reaction, there will be no effect. Reason is that there is no gas. Change in pressure does not affect the system when there is no gas. So once there is no gas, automatically it implies that if you want change the pressure, increase the pressure, decrease the pressure, it will not affect the system in any way. So a system can only be affected by pressure if there is at least one gas in that particular process. Now, the next thing that I think is worthy of note is the fact that if the number of moles of gases, note I did not say number of moles of reactants and products. I said the number of moles of gases on both sides of the equation are equal. Pressure change will not affect the system. If you notice that the pressure on this side is equal to the pressure on that side, that is, the number of moles of gases on one side is equal to the number of moles of gases on the other side, automatically you would not have an effect of change in pressure. So let's illustrate. Illustrating is a very popular reaction that we should know, and that is a reaction which involves combination of hydrogen and iodine. So this is a gas, this is a gas, and when they combine, it forms a gas. Iodine originally is a solid, but in this particular process, for its combination, it is in gaseous state. Now, how many moles of gases are on this side? One gas, which means we have 2 moles. On this side, how many moles of gases do we have? 2 moles. And once you notice that the number of moles of gases are equal on both sides, automatically there will be no effect of change in pressure in this system. So these are the basic things that you should take note of as we go further in our understanding of the concept. Now, having said this, let's go back to our slide and continue with our study. Now, with this said, you will notice, as we said and as you can see on the screen, pressure of gases is exerted as a result of collision between the gaseous molecules and the walls of the container. Hence, if the collision is increased, the pressure is increased and vice versa. So once I'm increasing the collision, automatically I'm increasing the pressure, which means if I'm decreasing the collision, automatically I'm decreasing the pressure. Volume, temperature, and number of moles changes causes a change in pressure. However, we are going to concentrate on the number of mole changes because that is exactly what is going to help us understand how pressure would affect the equilibrium position and give yield. Now, what is the effect of pressure changes? An increase in the number of moles will lead to an increase in the frequency of collision and consequently pressure. Hence, where there are more number of moles of gases, there will be more pressure and vice versa. So if the number of moles of gases are more, it means that that side there is more pressure. If the number of moles of gases are less, it means that that side there will be lower pressure. The question now is, how exactly does pressure change affect the system? Before we come to this particular note, I would like to say something. So let's look at the screen, basically. Let's go to our board, because this is a very important thing to take note of. If, for instance, the initial pressure of a system used to be 10 atm, and they said that this is when the system is in equilibrium, and for some reason I decided to go and increase the pressure from 10 to 20, please, what will the system do? It will decrease the pressure, because it needs to come back to this system at equilibrium. Now, if I now decide for whatever reason to decrease the pressure from 10 to something like 5, what will the system do? It will take it from that 5 and take it up back to 10. The question is not what the system would do, because it's very simple. If I do something, system does the opposite. But how it does this? Now, the system does this simply by favoring the side with more or less number of moles. Let's look at this. So if you consider this, looking at your screen, you will notice something. If the pressure of a system is increased, the system would have to reduce the pressure to restore equilibrium by favoring the side with less number of moles. So anytime you hear that the pressure of this system is increased, system will go and start reducing it. How will it reduce it? The side where there is less number of moles will be favored. Less number of moles means less pressure. More number of moles means more pressure. So whenever the system's pressure is generally increased, instead of going to the side where it will keep going higher and higher, it will go to the side where the number of moles is lesser. And once the number of moles is lesser, it means that there will be less pressure there. So let's consider a particular process to help us understand this. I'm going to have to go back and take this out for analysis sake. Okay. So if we consider this, for instance, now imagine, for instance, you have a particular process, 3A reacting to give 2B. Now, if this is a reversible process, note what I said, and I increase this system's pressure. When I increase it, system will need to decrease. If the system is going to decrease, it will go towards the side where there is decreased number of moles, and that is here, which means when I increase pressure for this reaction, system will favor the forward reaction. Why is it favoring the forward reaction? Because on this side there is less. When I increase, it needs to go where there is less. But on the other hand, when I now decrease, system will need to go where there is more pressure, and that is where there is more number of moles, which means it's going to go to the backward process. This is actually a very simple concept. Once you understand this, it makes these questions or answering questions with respect to this quite easy. Okay, having said that, we'll look at the second thing we are supposed to note. If the pressure of a system is decreased, the system increases the pressure to restore equilibrium by favoring the side with more number of moles. So the implication is that once you have a pressure decrease, once the pressure of a system is decreased, the system automatically goes towards the side where there are more number of moles to alter that particular process. Having said this, we are going to be answering some questions to help us understand this. Let's consider those questions. Let's start with this one. What will be the effect of increase in pressure on the following system at equilibrium? Increase in pressure. Now I'm going to write this equation properly so that we would actually understand exactly what happened here, because this is a typographical error. We'll correct that in our updated slide. But for now, let's just do this. Okay, so I have to remove this. So the original reaction, let me take this out, is NH3, 2NH3 reacting reversibly to give N2 plus 3H2. So that's that basically. And the question says, what will be the effect of increasing pressure in this particular system? So when I increase pressure, what is going to happen? So the first thing I need to know is if these things are gases. Yes, every one of these substances represented here is a gas. Then I'll now write out the number of moles. Number of moles on this side is 2. Number of moles on this side is 1 plus 3, which is 4. So here I have less number of moles. I have here more number of moles. So remember, they said that what will be the effect of an increase in pressure? So when I increase the pressure of this system, we already know that the system will decrease the pressure, which means it will favor the side with less number of moles, and that side with less number of moles would produce more ammonia. So with that said, let's look at the question. So it says option A, activation energy will decrease. Activation energy is decreased by catalyst and not necessarily change in pressure. Option B, the forward reaction will be favored. Obviously, it's not going to favor the forward because, as we said, since the pressure of the system was increased, system will need to decrease, which is going towards the side with lesser number of moles means decreased pressure. So which means it's going to favor this particular backward process. We're already sure that that's the answer. It's just to confirm. Okay, then option C, the concentration of ammonia. Ammonia is backward, so which means it is going to increase the amount of ammonia, and C is the correct answer. So you have that as that. Now, when you have a particular change in pressure, if the pressure is increased for a system will need to decrease it by going towards the side with less number of moles. But when you decrease the pressure, system will need to increase the pressure by going to the side with more number of moles. So your emphasis should be on the number of moles of gases on both sides when you are trying to understand the concept of pressure. Okay, so with that said, if we look at our options, our answer is going to be C. Why is it C? Because it's favoring backward reaction, which means yielding more ammonia. Hence, the concentration of ammonia will increase. Okay, we are going to try just one more question to buttress our understanding of this, and then we'll call it off. In which of the following reactions is the position of equilibrium not affected by an increase in pressure? So we are looking at the two conditions that would occur for pressure not to affect a system. Is number one, if the number of moles of gases in both reactions are equal, and then number two, if there is no gas at all. So let's look at option A. Option A has gases, but the gases on the reactant side are 4 moles of water gas, and on the product side 4 moles of hydrogen gas. Because the number of moles of gases on both sides are equal, automatically that's the answer. Remember, I did not say number of moles of substances, I emphasized the gases. So automatically your answer is going to be A. Why? The number of moles of gases on the reactant side, once it is equal to the number of moles of gases on the product side, you have that pressure does not affect the system. Let's go back to that particular slide to confirm that. So you notice this here. So also, if the number of moles of gases on both sides of the equation are equal, the pressure changes will not affect the system. So that's that basically. Okay, so we don't need to go further. That's basically our answer. You would see that in every other one there are either different number of moles of gases. Yes, in every other one there are different number of moles of gases. So with that, so let's just answer this final question and then we'll call it off in our study of equilibrium. The question says, when at equilibrium, which of these reactions below will shift to the right if the pressure is increased and the temperature kept constant? Please mind you, shifting towards the right is towards the product side, which means once you are shifting to the right, it means that you are favoring the product or formation of the product. Now, analyzing the question, when at equilibrium, which of the reactions will shift to the right if pressure is increased? Now, mind you, if pressure is increased, the system will need to decrease pressure, which is go to the side with less number of moles. So if it is going towards the side with less number of moles and that side is the right, it means that that right side has to have lesser number of moles of gases. Remember, they increase, so the system decreases. And if it's going to the right, it means that that right has to have less number of moles of gases. So let's consider A. Option A has 2 moles on the product, on the reactant, and 3 moles on the product. So that's not it, because we are looking for a particular answer where on the right side the number of moles of gases is lesser on the right side. Okay, option B has 2 moles of CO2 gas, but then on the product side it has 2 moles of CO and 1 mole, which is 3 moles, which is not the answer, obviously. Option C has it has 3 moles of hydrogen and oxygen, but on the product side it just has 2 moles. Yes, and that's the answer basically, because we said that when the system's pressure is increased, the system itself would decrease it by going towards the side where there is less number of moles. And if it is going towards the right, it means that the right side of the correct answer has to have lower number of moles. And since C has lesser number of moles of gases, remember, of gases on the product side, it's most likely the right candidate. But let's check D first. In D, you have 2 moles, 2 moles. What is likely going to happen in D is that pressure will not affect it. Why? Because the number of moles of gases in both systems are equal. I presume you've learned a lot on chemical equilibrium with these studies. Remember, this is Efiwe, where excellence is attained without stress. Don't forget to do your test questions and also download the app if you don't have it. Thank you very much.